Chapter 4 continued, 3 major classes of chemical reactions, Section 4.3, precipitation reactions. The first type of chemical reactions we are going to look at are the precipitation reactions. A precipitation reaction is a reaction in which two soluble ionic compounds form an insoluble product, a precipitate, that falls out of solution. The reaction between silver nitrate and sodium chromate is an example of a precipitation reaction. This slide shows what would happen when an aqueous solution of sodium fluoride is added to an aqueous solution of calcium chloride. The calcium ion and the fluoride ion will come together to form calcium fluoride, which is not soluble in water and will precipitate out of solution. The sodium ion and the chloride ions are spectator ions and do not participate in the reaction. Therefore, the key event in a precipitation reaction is the formation of an insoluble product. So when we mix aqueous solutions of two ionic compounds, how can we tell if a precipitate will form or not? To predict whether or not a precipitate will form, follow these 3 steps. 1. Note the ions present in the reactants. Consider the possible cation-anion combinations. And third, decide whether any of the combinations is insoluble by using the solubility rules given in Table 4.1. Table 4.1 provides a short list of solubility rules to help us predict whether or not a precipitate will form. It is not necessary to memorize this table since all quizzes and exams are open book and open notes, but you should become familiar with how to use it. You may want to have a copy of this close by when taking the weekly quiz and the midterm exam, as you do not want to waste valuable time searching for this table during your timed assessment. The table is broken up into 2 parts, soluble ionic compounds and insoluble ionic compounds. The rule is given first, followed by any exceptions to the rule. The first rule states that any compound that contains a group 1 metal or the ammonium ion will always be soluble, no exceptions. The second rule states that all compounds that contains the nitrate ion, the acetate ion, and most perchlorate ions will always be soluble. The third rule states that compounds that contain the bromide, chloride, or iodide ion will always be soluble. Exceptions include those of silver ions, the lead 2 ion, copper 1 ions, and mercury 1 ions. All compounds that contain the fluoride ion are soluble except those of lead 2 ions and all group 2 metals. The last of the soluble ionic compound rule states that all compounds that contain the sulfate ion are soluble except those of calcium, strontium, barium, silver, and lead 2 ions. The next 3 rules pertain to those ionic compounds that will always be insoluble in water and the exception to these rules. The first rule states that all compounds that contain the hydroxide ion are insoluble except those with group 1 metals and the larger members of group 2 metals beginning with calcium. The second rule states that all compounds that contain the carbonate ion are also insoluble except for those with the group 1 metals and the ammonium ion. The third and last rule states that all compounds that contain the sulfide ion are insoluble except those of group 1 and group 2 metals and the ammonium ion. Let's take a look at this a little closer by looking at what happens when solutions of sodium iodide and lead 2 nitrate are mixed. The unbalanced reaction of sodium iodide with lead 2 nitrate, which will produce solid lead iodide and aqueous sodium nitrate, is given first. Step 1 tells us to note the ions present in the reactants. We have the sodium cations, the iodide anions, the lead 2 cations, and the nitrate anions. Step 2 tells us to consider the possible cation-anion combinations. One possible combination is to put the sodium back with the iodide and the lead 2 ion back with the nitrate, but this would just give us back our reactants. The other combination is to combine the sodium with the nitrate and the lead 2 with the iodide. This is how we can tell that the first chemical reaction was not balanced. In the first equation, we are showing the relationship between sodium iodide and lead-2 nitrate to be 1:1 when it's not. The relationship between these two reactants is actually 2:1. For every 1 mole of lead-2 nitrate we also need 2 moles of sodium iodide to react with it. The second equation on this slide is the correct balanced molecular equation for this reaction. Step 3 tells us to decide if any of the combinations are insoluble. According to the solubility rules given to us in Table 4.1 of your book, tells us that lead-2 iodide is not soluble and will precipitate out of solution. So one last thing about this equation, just notice that the ions are exchanging partners. As we mentioned earlier, reactions such as this are called double displacement or metatheses reactions. A double displacement or metatheses reaction is a reaction in which atoms or ions of two compounds exchange bonding partners. Okay, now it's time to work through a problem. Our sample problem wants us to predict whether or not a precipitation reaction has taken place. If we have determined that a precipitation reaction has in fact taken place, then we are asked to write a molecular, total ionic, and net ionic equation and to identify the spectator ions. Our strategy is pretty straightforward here. We need to convert the names of the reactants to chemical formulas. We are looking to see if a precipitation reaction has taken place, so we know we are dealing with a double displacement reaction. Once you have the chemical formulas for your reactants, exchange partners to get the chemical formulas for the products. Make sure you have enough of each ion to make the ionic compound neutral. Using the solubility rule, see if any of the products are insoluble. If no precipitate forms, you're done. If a precipitate forms, you will need to write a total ionic equation, cancel out all your spectator ions, and then write the resulting net ionic equation. Please work through this problem following this strategy we just developed before moving on to the next slide where you can check your work. Here is the solution for part A. Did you predict that strontium fluoride is not soluble in water and will precipitate out of solution? Were you able to come up with the correct total ionic and net ionic equations? If not, are you able to see this now that you have the solution? If you cannot see where you went wrong and you are still confused, make sure that you contact me and we will work through this problem together. Now try part B and then check your work on the next slide. Notice in part B, all the reactants and products are soluble in water. Therefore, this is not a precipitation reaction because all the products are soluble and all the ions are spectator ions. Do you see this? Now work through the follow-up problem and let me know if you have any questions. Here is another sample problem, but this one is a little different than the one we just worked. Here we are asked to use molecular depictions to see if we can determine which of the following compounds are dissolved in water. Here is our strategy. Note the number and charge of each kind of ion and use table 4.1 to determine the ion combinations that are soluble. Notice the charges of the ions in beaker A are 1 plus and 2 minus. Which one of the possible compounds listed for part A will form these ions in solution? Notice that the charges of the ions in beaker B are 2 plus and 1 minus. Which one of the compounds listed for part B will form these ions in solution? Then do a double displacement reaction to form the products. Look at table 4.1 to see if the products will be soluble or not. Please work through this problem and see if you can determine the compound that is dissolved in beakers A and B before moving on to the next slide. Were you able to determine that the compound dissolved in beaker A is sodium sulfate and the compound dissolved in beaker B is barium nitrate? If not, please go back to the previous slide and determine which of the following compounds are soluble in water. If you determine a compound is not soluble in water, it cannot be the correct answer. Once you have determined which compounds are soluble, dissociate them into their ions and see which compound best matches the ions in solution. For part C, consider the cation and anion combinations from the two solutions and use the solubility table to decide if either of these is not soluble in water. Notice that of the possible combination, only barium sulfate is not soluble in water. Please try to write the molecular, total ionic, and net ionic equations before moving on to the next slide where you can check your work. If you need help, you can either contact me or move on to the next slide. Here are the solutions to the three equations. For the molecular equation, the total ionic, and the net ionic equations. Were you able to come up with these equations? If not, do you understand now that you've seen the solutions? Please let me know if you need any help. In Part D, we are asked to determine what is the maximum mass of precipitate that can form if each particle represents 0.010 mole. We have the equations that we need to help us with this on the previous slide. Now that we have these equations, we can count the number of each kind of ion that combines to form the solid. Multiply the number of each reactant ion by 0.010 moles and calculate the molar product formed from each. Decide which ion is the limiting reactant and use this information to calculate the mass of product formed. Try doing this even though the solution is given to you on the bottom of this slide. Notice that the barium ion will produce the product in the smallest amount and therefore is the limiting reactant. Using moles of barium sulfate formed from the barium ion, calculate the maximum amount of barium sulfate that can form. Okay, so here is the answer. Were you able to come up with this answer? If not, can you follow the steps in the solution to see how the author came up with the correct answer? Make sure you work through the follow-up problem before moving on to the next slide. Also, please be sure to get in contact with me if you have any questions or concerns. Here is another sample problem that may be a little different than the others. In this problem, we are asked to find the amount of magnesium hydroxide that would form when a known volume and concentration of one reactant reacts with excess of another reactant. Let's develop our strategy for solving this problem. First, we need to convert the chemical statement into a balanced chemical equation. Then, using the volume and molarity of magnesium chloride, we need to find the number of moles of this reactant. Once we know moles of magnesium chloride, we can use the balanced chemical equation to find moles of magnesium hydroxide, and then use the molar mass to convert moles of magnesium hydroxide to grams. That's our strategy. Now please work through this problem before moving on to the next slide. Here is the roadmap for our strategy. Notice between each step is further information on how to get from one step to the next. Here are the solutions to get to moles of magnesium hydroxide from the volume and concentration of the magnesium chloride solution. Were you able to come up with the correct number of moles of magnesium hydroxide? If yes, great job. You can go on to the next slide. If no, can you find your mistake? Please let me know if you need any help with this problem up to this point. When you are ready, please go to the next slide where you can check your work for the last conversion. And finally, we are done. Here are the number of grams of magnesium hydroxide that can be formed from the magnesium chloride solution. Were you able to come up with the correct answer? Again, if yes, great job. If no, and you cannot figure out where you went off track, please let me know so that I can help you. This is figure 4.10, and it provides you with a summary of the amount, mass, number relationships for a chemical reaction in solution. You may want to have this available when you are working problems, taking the weekly quiz, the midterm exam, and the final exam. Here is another sample problem that will give you practice with the different relationships we have been discussing so far in this chapter. In this problem, you are asked to find how many grams of mercury 2 sulfide will form when a solution of mercury 2 nitrate reacts with a solution of sodium sulfide. What is your plan for solving this problem? Think about it for a minute and write down a few pointers, and then we could go over the suggested strategy for solving this problem. If you started your plan with writing a balanced chemical equation, you are spot on. Next, we need to determine which reactant is the limiting reactant. In order to do this, use the molarity data to find moles of each reactant, and then use the balanced chemical equation to find moles of product. Remember, whichever reactant produces the product in the smallest mole amount will be the limiting reactant. Once you find moles of limiting reactant, convert moles to grams, and you are done. This slide shows you which reactant is the limiting reactant. Were you able to come up with the right limiting reactant? If not, can you see where you might have gone off track? Now that you have moles of product, convert to grams and compare your answer to the one shown here. Let me know if you have any questions or concerns. Just in case you like to use reaction tables, here is the reaction table for this sample problem. Remember, for now, you do not need to use reaction tables. Once we get into the second semester of this course, we will be required to use them in several chapters, so it may not be a bad idea to get familiar with them. This is the end of the material we will cover in week 6, which covered sections 4.1 through 4.3 in chapter 4. Please work as many of the end of the chapter problems you feel is necessary until you have mastered the concepts presented during this lecture. Once you are comfortable with the material, please take the weekly quiz. Then complete the lab assignment and then take the lab quiz. Next, we will cover the rest of the material presented in chapter 4, specifically sections 4.4 through 4.7.